Today, we want to talk about the binomial series. Remember what we're doing with all these Taylor series. We want to be able to construct a Taylor series without having to take all the derivatives. So we learned some common ones, e to the x, cosine x, and sine x. And we learned that we can just manipulate those, start manipulating them instead of taking derivatives. Because Taylor's formula requires, if we want to go to an nth degree, we need to go with find n derivatives. We don't want to have to do that because taking derivatives, easy as it is, gets a little bit cumbersome after a while. Sometimes people say, well, we can just use a machine to find the derivatives. If we're going to use a machine to find the derivatives, we might as well just have that same machine find us the Taylor series. So that's not the issue. But what we want to do is find building blocks that we can use to build more functions. So let's build another important building block, the binomial series. So we're going to start off with f of x is 1 plus x to the p. And we need f of 0 is going to be 1. We need to take a bunch of derivatives and then plug in 0. Look for a pattern while we're doing it. We don't want to just mindlessly take derivatives and plug in 0. Although that could be, I don't know, maybe that's how you chill out. I don't know. No judgment. Now in the crime movies, like there's like the criminal and he's like doing crazy criminal stuff. It's like, oh, we need to get into this person's mind. Then they break into his house and then they find a notebook and it's all got all kinds of crazy ramblings and scribblings on it. It's like a little manifesto. If I ever turn criminal and you break into my office, you're going to find like those composition books and they're just going to be filled with integrals. And that's going to be my crazy scribbling. Oh my God. Do you see this? This man is clearly unhinged. What is it? Crazy scribblings? No. He's just integrating functions. A monster. You know how it is? I don't know. I don't judge what you do to relax, so back off. So we take the derivative, p times 1 plus x to the p minus 1. And what we're going to notice is that the 1 plus x to the exponent part is not going to, is always just going to be 1 when we plug in 0. That's why we picked it. So it's these coefficients that are going to show up for our derivatives. Our second derivative will be p times p minus 1 times 1 plus x to the p minus 2. Multiply by the exponent, subtract 1 from the exponent. So we can quickly see what's going to be happening here. The first derivative had p. The second derivative had p times p minus 1. The third derivative is going to have p times p minus 1 times p minus 2. So we can see how this is going to go. And then the fourth derivative will have the first 4 factors of p factorial. So the nth derivative of f at 0 will be the first n factors of p factorial. So it's going to start off at p, then p minus 1, p minus 2, and then it stops, not when it gets to p minus n, but when it gets to p minus n plus 1, because we start off by subtracting 0. So that's why we have p minus n plus 1. So in general, so when n is 4, we stop at p minus 3. So that would be when when n is n, we stop at not p minus n, but p minus n plus 1. Because the first one is p minus 0. The nth derivative has the first n factors of p factorial. So now if I have a function, of this form, 1 plus x to the p, oh, I should write it down, I guess. It starts off with 1 plus p times x. This is a Taylor series around 0. Then the next coefficient will be p times p minus 1 over 2 factorial x squared. And then p times p minus 1 times p minus 2 over 3 factorial x cubed, and so on. We have powers of x because we're building the series near x equals 0, so it's in terms of x minus 0, x. And we found the pattern for building the Taylor series. All we're filling in is the numerator. That's the only part that changes when we're building a Taylor series, that fn at a. Then it's over n factorial. That's always the same, times x minus a to the n, and that's always the same. The idea is that we don't want to have to take all these derivatives all the time. So let's suppose that our function f of x is the square root of 1 plus x. What we can notice here is that this is binomial with p equal to 1/2. So we will read this as 1 plus x to the 1/2 power. So I'm just going to start following Taylor's formula. And p is 1/2, so plus 1/2 on x. The next coefficient is going to be 1/2 times 1/2 minus 1. Over 2 factorial. times x squared. Then the next term will be a half times a negative a half times a negative 3 halves. Margins on the right side always get cheated by generous margins on the left. I knew this was going to take forever. This is why I bailed after 4 terms. But then I'm like, well, this might give us a false pattern, so I'm going to throw in that. Any questions? We would need to simplify this for, but that's how we build using the binomial. Yes.
So we have like what's the plus one?
That's telling us where we stop. So notice that the third derivative stopped at p minus 2, and the fourth derivative stopped at p minus 3. So in general, the nth derivative will stop at not p minus n plus 1. The other way to think about that is we start the counting. We have 4 factors, but we start the counting at minus 0. So minus 0, 1, 2, 3. So even though there are 4 factors, the last one has a minus 3 attached. So we need to simplify these, but we get a 1 plus a 1/2 x. This is going to be a minus. Half times a negative a half is going to be a minus. And there's a 2 times a 2 times another 2. So a 1/8 x squared. The next term will be positive because there's 2 negatives. And we'll have in the denominator 2 times 2 times 2 times 3 times 2. But one of the 3's will cancel out. So we have 1, 2, 3, 4 2s. 1/16 x to the third. The next term will be negative because there are 3 negatives. We have in the denominator 2, 2, 2, 2, a 4, a 3, and a 2. And one of the 3's will cancel out. So I have 5 over 1, 2, 3, 4, 5, 6, 7 2's. What's 2 to the 7th? I don't have to know. I probably should know, but I'm going to be off one in one direction. Arithmetic isn't my strong suit. There's 7 because the 4 has 2 2's. And we got rid of the 3 from the factorial. Is it 128? 2 to the 5th is 32. 64, 128. I was going to say 128 too. I didn't trust myself. Any questions? Right now, we don't see a pattern, but that's okay. We can just build more terms. If we find that this approximation is not close enough, if this doesn't give us the epsilon we want, we can just start adding more terms. Any questions? All we have to do is figure out where things are going to start. Let's suppose that we have g of x is 1 over the square root of 1 plus x. We want to write things as a power of a binomial whenever we can. So I'm going to write this as 1 plus x to the negative 1/2. So in this case, p will be negative 1/2. So now p is negative 1/2. So my first term will be negative 1/2 x. Then when we start off at negative 1/2, I'll have a negative 1/2 times negative 3/2 over 2 factorial x squared. Then the next term will be a negative 1/2 times a negative 3/2 times a negative 5/2 over 3 factorial x cubed. And then I'll have 4 factors, starting off at negative 1/2 times negative 3/2 times negative 5/2 times negative 7/2 over 4 factorial x to the 4. Then, of course, we're going to want to clean these up. Because this looks awful. So I have 1 minus 1/2 x. The next term will be positive because I have 2 negatives. So 1/2 times 3/2. I have a 3 in the numerator and 2 times 2 times 2 in the denominator. So plus 3/8 x squared. The next term will be negative because there's 3 negatives. And here the 3's cancel out a term earlier than they did in the previous one. But we still have a 5 in the numerator and a 2, 2, 2, and another 2. So minus 5/16. And then we'll look at the next term, which will be 4 negatives, which is a positive. The 3 cancels out of a 4 factorial. So I'm going to have a 5 and a 7 left over. And I've got 1, 2, 3, 4, 5, 6, 7 factors of 2. Presumably, the next term will be negative. So I'll write negative and then dot, dot, dot. Question? How's everybody okay? Of course, this is just like subtracting 1 a bunch of times. It's fractions, ooh, but it's still just subtracting 1. The trickiest part is not the subtracting of the 1. The trickiest part is simplifying our coefficients. Because we're new to these factorials, and we have to remember that 4 has a 4, a 3, a 2, and a 1. So when I look at this 4 factorial, there's a 4, a 3, a 2. I don't have to write the 1. And so the 3 is canceling. And so the denominator is 4, 2, and then 4 more 2s. So 2, 3, 4, 5, 6, 7 2s. Over here, the 3 factorial is a 3 times 2. So the 3 cancels, but that leaves a 5. And I have 4 2s in the denominator. How's everybody? Okay. This part is usually the thing that Calc students are good at. Here is a process. Copy this process. In problems 1 through 20, just do what happened in example 1. In problems 21 through 40, do what happened in example 2 with these new numbers and new powers of x. And everybody's like, oh man, this is my favorite kind of math where I don't really have to do that much math. Students that don't balk at homework assignments that look like in problems 1 through 10, do the same thing. In problems 11 through 20, yeah, do more of the same thing. You can tell, all I have to do is begin, I don't know what it would be, but it used to be that I would just use World of Warcraft. Hey, does anybody play World of Warcraft? And I can immediately tell who's going to be perfectly fine with super repetitive homework assignments. Because they play a game where it's just the same thing over and over again. I successfully managed to not get into League of Legends, so there's a plus. Also, isn't League of Legends primarily like a PvP game? That's the other reason that I can't get into it. I would just be a liability to my team. Back in the World of Warcraft days, I could barely keep pace. I'd be like, ugh, sorry guys, I'm old. And they're like, oh, we can tell. Never mind if I'm playing like an online game and there are other players that might be shooting at me. Because I'm just going to be like, I don't know, easy targets. Anyway, what are we talking about? Oh yeah. I'm not good at online gunfights, but if there was a game based on integration, I would mop the floor with these moves. Because by the time you're like thinking, oh, I think I should do substitute, I've already got you. And I'm going over to the spawn point. It's like, well, you might as well just log off now. You know what I mean? Anyway, what are we talking about? Oh, yes. So the idea is we don't want to be taking derivatives. We took derivatives to find our pattern for how to build a binomial series. And we haven't had to take derivatives since. We just had to subtract 1. So let's suppose that we had another function, super complicated. This has a variation on the previous one. It's binomial. I see 2 terms being raised to a power, but it's not 1 plus x, it's 1 minus, and it's an x squared. So I'm changing 2 things at once. This is very dangerous. So our p is -1/2, just like before. But now I'm going to make the transfer. I'm going to make the extra substitution. I'm going to trade up my x for a negative x squared. So I'm going to trade x for a negative x squared. But other than that, I can just use the one that we just found. Because it has the same p of -1/2. I'm just going to grab my series, the Taylor series before. And it's going to be 1 minus 1/2, but instead of x, I'm going to write negative x squared plus 3/8 times negative x squared minus 5/16 times negative x squared cubed plus 35 over 128 times negative x squared to the 4th. I'm going to grab the binomial series that we built for p equals negative 1/2, and we're going to replace the x minus x squared. We want to avoid taking derivatives. And then we can just simplify. Now this is going to be a plus 1/2 x squared. This negative gets squared, so it becomes plus 3/8 x to the 4th. This negative gets to the third power is negative, times a negative makes it positive. And then we'll have 5/16 x to the 6th. And then plus 35, 128 x to the 8th, and so on. We're trying to avoid having to take all the friggin' derivatives. We're in derivative class, so we don't have to do derivatives anymore. We're in integral class, so we don't have to find all these friggin' integrals. We don't want to have to write stuff down. We just want to know what is going to happen. If we were to start off by taking derivatives, just to get these 5 terms, we would have to take 8 derivatives, because the product rule is going to keep throwing x's as factors. And then when we plug in 0, a lot of terms are going to get zeroed out. If this was an x cubed like we used yesterday, then this would be all the way out to x to the 12th. We'd have to take 12 derivatives just to get 5 terms. Because the product rule, and the chain rule actually, because the chain rule is going to throw out an x to the 3rd every time we take the derivative of 1 minus x to the 3rd for the derivative of the inside. And then it's going to take 2 more derivatives for that x to the 3rd to go away to give us a term that doesn't just go to 0. Any questions? We should always be on the lookout for other functions that we can get without having to take some derivatives. So this one seems very different. But if we take the first derivative, h prime of x is 1 over the square root of 1 minus x squared, which is the Taylor series that we just found. It's like I planned this shit or something. I also called it capital H. Everybody know what Chekhov's gun is? In storytelling, Chekhov's gun is if you put a gun on the table in Act 1, it has to go off by the 3rd act. I might have the acts wrong. You see it all the time. Some writers think that they're foreshadowing when they're just telling you that something is going to happen. Like when a character makes an offhand remark, it's like, oh, no. I was an excellent Boy Scout. I know how to survive in the woods. I wonder if that will come up because they wouldn't have said it otherwise. It's kind of like everybody familiar with Scooby-Doo? Scooby-Doo is hyper-efficient storytelling. There's the Scooby Gang and two other characters. One of those other characters is the ghost. Here's how to tell if of the two other characters, the handsome one is not the ghost. That's it. If one of the characters is the sheriff and he's drawn like Batman with a gigantic square chin, well, oh, it's the other guy. You know what I mean? Figuring it out is not the point for the audience. Figuring out is the point for the Scooby Gang. But there's no fact in the Scooby-Doo mystery. You know what I mean? It's kind of like also Law and Order. See, also Law and Order. They start introducing characters. You know who the guilty party is. It's not supposed to be a mystery. Same kind of thing. Scooby Gang is solving a mystery because they're the characters, but the audience already knows what's going on. So, oh, I wonder why he called it capital H. Isn't arcsine related to this 1 over the square root of 1 minus x squared? And yeah, it is. The first thing we would do is find the first derivative. So instead of taking all these derivatives, plugging in 0, because we know we would need a bunch of derivatives just to get to where we need to go, I'm just going to notice that the derivative of arcsine is 1 over square root of 1 minus x squared, and we conveniently still have that one on the same page. So I'm just going to integrate that. So the integral of 1 is x. The integral of x squared is a third x cubed. The integral of x to the fourth is a fifth x to the fifth. The integral of x to the sixth is 1/7 x to the seventh. Now, when we're integrating, we should have a plus c. It would look ridiculous to put the plus c at the end here because we don't want to write it after the dot, dot, dot. Because if we put plus c at the end here, that would say keep going until you get to a constant. And that's the wrong direction. C is the 0-degree term. Don't put it at the end. Just lead with that. We don't actually need to see. We don't actually need to see because what's the first term in the Taylor series for arcsine of x? It's going to be h of 0. So we don't actually need the plus. Any questions? Yeah. Yes, because we don't want to take a bunch of derivatives of arc sine. And we notice that arc sine is just the integral of 1 over the square root of 1 minus x squared. Since I already have the series for the or 1 over square root of 1 minus x squared, if we just integrate that series, we'll get the series for arc sine. This is the same thing that we did when we found the Taylor series for sine and then the Taylor series for cosine. Just took the derivative of the Taylor series for sine to find the Taylor series for cosine. And cosine is the derivative of sine. Good questions. So if we think of the other function that has this characteristic, arctangent, the derivative of tangent is 1 over 1 plus x squared. So the derivative f prime is 1 over 1 plus x squared, which is binomial with p equal to 1/2 and trade your x for an x squared. Sorry, p equals -1. Then integrate. How's everybody okay? So we set up the binomial and we had 1 plus x. That was our basic binomial series with a 1 plus x. What if we have a binomial and the constant is not 1? We know what to do if the variable part is not just plus x. When it was minus x squared, I just acted as if it was plus x and then traded my x for a minus x squared. So that part we can solve. But what if the coefficient in front, or sorry, not the coefficient, what if the constant term is not 1? Here's one of those instances in math where it actually works if I just tell you what the answer is. Most of the time, if I tell you what the answer is, that doesn't work. It just gets in the way of you actually learning a thing. But here's one of those instances. If I just tell you what the answer is and how to deal with this not 1 constant term, it actually helps and makes all of Calc 2 snap into focus. And forever, you'll never have trouble integrating anything, even though it doesn't seem related. In fact, if I just tell you what to do with that 4 instead of a 1, Calc 3, you'll get an automatic A. You won't even have to work hard. It'll just come natural. Be like Wesley Snipes in Demolition Man. It's like, well, I'm possessed. You just start doing conflict. But I have to tell you right now what that is. I have to tell you right now how to deal with that 4 when it's not a 1. So here goes. Be ready to have all of math make sense forever. Everybody ready? Oh, dang, look at the time. We're out of time. I guess it's going to be just difficult like normal. That's it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing.